Okay, so this will be the carbohydrate cow, and we will feed the cow non-structural carbohydrates first. So we feed our cow non-structural carbohydrates. Just make it go all the way through. Okay, and in the mouth, like always, we're gonna have a decrease in particle size. We'll come back and talk about saliva here after a second, or after a few minutes. So in the rumen, microbes are going to take the non-structural carbohydrates, whether they're disaccharides, starch, whatever they are, and they're going to ferment them into acetate, propionate, and butyrate. Okay, we're also going to produce CO2, CH4, and MCP. Okay, the CO2 and CH4 are going to be eructated back out, which we're disappointed about because the CH4 represents an energy loss from the animal. The MCP is going to go to the small intestine, so we're going to go ahead and draw that because this will come in useful in the next section. And it's going to be digested and absorbed. Okay, so we got that captured. And on this acetate and propionate and butyrate, we're going to say they produce 55% acetate, 35% propionate, and 10% butyrate. The numbers aren't really crucial. What's crucial is you know that the proportion of propionate is greater when we're fermenting starch or non-structural carbohydrates than when we're fermenting structural carbohydrates. These are going to go up here, and we're going to set them right here and absorb them in a minute. Okay, down here we're going to write the microbial enzymes. For starch. Okay, and those enzymes are amylase. And there are two. There's alpha, which is an endo enzyme, and there's beta, which is an exo enzyme. Okay, and after amylase, we have glucoamylase, polylinase, which is a debranching enzyme, so it breaks the 1,6 bonds. We have isomaltase, which also breaks the alpha 1,6 bonds. Maltase. Ugh. And then we have maltase. So those are the microbial enzymes for starch degradation, and then the starch is going to get fermented into acetate, propionate, and butyrate. We said some fraction of that starch is not going to get fermented, so it's going to show up at the small intestine. The sucrose and the lactose in a mature ruminant isn't going to make it to the rumen or to the small intestine, but the starch does. And we have pancreatic alpha amylase. And pancreatic alpha amylase, remember, is secreted in limited amounts in the cow, so that's going to be a barrier to digestion. The other thing to remember from the pancreas is the production of buffer to raise the pH and also provide sodium for the absorption of glucose. And then we have our brush border enzymes. And our brush border enzymes are going to be glucoamylase, maltase, and isomaltase. In a nursing ruminant, we would have lactase and fluorizin hydrolase. Okay, and so those two would be in the nursing ruminant. And remember, the milk is going to bypass the rumen, so it's not going to be fermented, so you're going to directly digest the lactose in the ruminant animal. But in the adult, it's just starch being digested, so we have glucose. And then we can draw our enterocyte again, and this will be a simpler enterocyte. Because we only have to absorb glucose, and that gets absorbed through SGLT1. Then we have GLUT2. Getting it the rest of the way out. And then that glucose that's been absorbed is going to go to the liver. Okay. Not all the starch that makes it to the small intestine is going to be digested in the small intestine. So again, we're going to have fermentation using the microbial enzymes that we discussed earlier, and we'll produce acetate, propionate, and butyrate. And those three will get absorbed. We'll also have the production of CO2, methane, and MCP, all of which get excreted. And again, while we're here, we'll make a note for butyrate. Butyrate is an energy source for epithelial tissue. Epithelial tissue of fermentation chambers. Okay, so that means in the rumen and the large intestine that the butyrate is going to be used by the epithelial tissues as a source of energy. And so if you want really big, healthy papillae in the rumen, you feed them sugars that produce more butyrate, and the result is you get bigger papillae. Okay. Before we leave non-structural carbohydrates, we're going to come down here and we're going to draw starch, or write the word starch. And again, amylose, amylopectin, become oligosaccharides, become maltose, maltotriose, maltotriose, isomaltose. All of these become glucose, and in the rumen and large I, we have fermentation, and that produces acetate, propionate, and butyrate. And the small I, we get to absorb glucose. Okay. Now we're going to come back to the mouth. We're going to feed our cow structural carbohydrates. Draw the line all the way through. And in the rumen, the structural carbohydrates are going to be fermented. We'll produce acetate, propionate, and butyrate, and we'll say 70%, 20%, 10%. Again, the numbers are probably wrong, but the idea is to get a sense of the differences, that we're producing more acetate here than when we were digesting or fermenting starch, and less propionate than when we were fermenting starch. Still going to produce CO2, CH4. We're going to produce more CH4 because we're producing more acetate, and we're also producing microbial crude protein. Probably less microbial crude protein because the extent of digestion is generally less. Some things up here that we want to get in this decrease in particle size is we get increased rumination with structural carbohydrates, which increases pH. Okay, because when we ruminate, we add buffer, and that's going to increase the pH of the rumen. Okay, these guys are going to get absorbed, and they're going to go to the liver. So both acetate, propionate, and butyrate from structural and non-structural carbohydrates are absorbed, go to the liver. Again, remember, butyrate is going to be used by the epithelial tissue to make the papillae grow. And the rumen and the large intestine, cellulose is going to become oligosaccharide, which is going to become cellobiose, which is going to become glucose, which will then be fermented to acetate, propionate, butyrate is what you're going to absorb. We also have CO2 and methane, and this can take place in the large intestine and the rumen. Okay, so any fermentation chamber can do that. Rumen going to be better at it because the feedstuffs have longer to be there. Nothing's going to happen in the small intestine. Nothing happening. We show up at the large intestine again. Acetate, propionate, butyrate, CO2, MCP also getting produced. Both of these get absorbed, and they're also going to go to the liver. Okay, the liver can release VFA metabolites, from acetate and butyrate, and those are going to be used by the ruminant animal for the synthesis of subcutaneous fat, milk fat, and very importantly, energy. Okay, the other thing that can be released is glucose from propionate, And glucose can also be released as glucose from the small intestine. This glucose is important, especially in the beef cattle industry, because we can use it for the synthesis, so the cow can use it, the animal can use it for the synthesis of marbling, and also to meet its energy demands. Okay, just like in the non-ruminant, this glucose can act on the pancreas, and the pancreas can produce insulin, and the insulin is going to increase glucose absorption by muscle and adipose, and the result, or using GLUT4, and the result of that is a decrease in blood glucose concentration. Okay? It doesn't show up so well. There, that looks better. Okay, let's see if I got everything we need to make sure and have. We're gonna talk for 2 seconds about lignin. I'll do it down here, that way you guys can still see that. Lignin, not fermented, not digested, not a carbohydrate. Okay, good deal.